In this lecture, we'll convert the small-type angle solution to a k-space integral, and then we'll talk about how to design two-dimensional spiral RF pulses. Okay, so let's refresh our memories on the small-tip angle solution. The small-tip angle solution that we derived in a previous lecture involved an integral over time, wherein the excited magnetization at a given time t is equal to the integral of the RF pulse from the beginning of the pulse up to this time t, multiplied by the complex exponential that applies the complex weighting due to the gradients. So this is a function of time of the RF pulse, but there's a problem with this in that we don't specify the target patterns we want to excite as a function of time. We specify them as a function of space, so they are in the image domain. Sorry, let me switch colors. And then we Fourier transform to get them to the k-space domain, which we want to then relate to the temporal samples of the RF pulse. So we have some dimensional conversion issues that we need to take care of here. And we'd like to be able to express the waveform as either a function of time or k-space location. We'd like to flexibly be able to go between these two dimensions. So let's do that. So we can equivalently rewrite the integral on the previous slide or the complex exponential in the small tip angle integral as an integral over a delta function multiplied by all the k-space locations. Right? So the delta function, this is an integral over all of k-space, and the complex exponential then can be visiting any k-space location, but we multiply it by a delta function that sets it to 0 if we're not at some position along the trajectory. Okay? And this relationship holds by the sifting property of the delta function. This is why we can equivalently express this complex exponential as this integral. Okay, so we can make that replacement and we get this expression. Then we can swap the orders of integration between the k-space integral and the time integral and arrive at this expression, right? We took time and moved it in and k-space and moved it out. And now we can call this overall term here, where we have the integral of the RF pulse over time times the delta function. We can call that all a function p of k, right? It integrates out the time dimension, and we're left with just a dependence on k. So the magnetization then is the inverse Fourier transform of this p of k function. This is where we really concretely establish the Fourier transform relationship between the RF pulse and the excited magnetization. So, and now we really have what we need. So given a target MXY pattern that we want to excite, it's easy to get P of K by inverse Fourier transform, right? So we can use the fact that it depends on K to get P of K. So now let's see how we can tease out B1 of T from P of K. That's the remaining step that we need in order to specify fully an RF pulse. So I've rewritten the expression for P of K here. Now what we're going to do is we're going to multiply and divide within the integral by the derivative of k as a function of time. So that is k prime of t is going to be d tau k of tau comma t. And if we apply that, then we get this expression, right? We're going to have a k prime of t here and a k prime of t here. Now we're going to label this entire expression w of k of t, and this guy turns out to be a unit delta function. That is, if you evaluate the integral over time, you would get 1 here at the k-space location, locations, and 0 elsewhere. So this integrates now to a proper delta function. So what we've done here then is made the implicit weighting due to the varying velocity with which k-space is scanned explicit. Right, the velocity being this time derivative of k. So what is k prime of t? It is equal to the magnitude of gamma times g of t, right? Since k is the integral of the gradient, that's what we get. And we call w of k of t a weighting function. And so now p of k is equal to this weighting function times the delta function and times the velocity. And so we'll note here that w of k of t is defined only on the trajectory. That is, it's undefined for k's that are not visited by the trajectory, right? We can't evaluate the derivative if we're not on the trajectory. And if we now assume that the trajectory does not cross itself, so that w of k, the weighting function, only has one value at each point k, then we can pull it outside of the integral, right? So it now becomes independent of time. We can pull it outside the integral. And the remainder of the integral we call s of k, which is a sampling function, like a bed of nails. Again, time is integrated out, so this is only a function of k. And we can do this because any arbitrary function f of x times a delta function that's centered at x naught is equal to that function evaluated at x naught also times that delta function. Okay, so equivalently we can evaluate w only at this location k and pull it outside the integral, because it becomes, when we do that, it becomes independent of time. Okay, so we have now that the excited magnetization, putting this together, we have now that the excited magnetization is equal to the Fourier transform of this w of k weighting function times the sampling function, right? This is just ends up being ones at the locations we visit with the trajectory and zeros elsewhere, times the complex exponential from the k-space weighting, and then integrating over all k-space. Where here again the weighting function is b1 of tau divided by k prime of t comma tau, and s of k, the sampling function, is minus infinity to t delta cubed k of tau comma t minus k times the absolute value of the derivative of k. And then there's a d tau here. So now we can see how we can design an RF pulse given a k-space trajectory, a defined k-space trajectory that's generated by specific gradient waveforms, and a target pattern that we want to excite. First, we define a target MXY pattern and calculate its Fourier transform. That gives us the k-space weighting function that we want to achieve, that we want our pulse to produce. Then we evaluate that k-space weighting function on the trajectory locations defined by the gradient trajectory, the gradient waveforms, which is k of tau comma t. This then gives us w of k of tau comma t. That is the pattern that we want evaluated on that trajectory. Finally, we just scale that by the k-space velocity to get the overall waveform. So then b1 of t will then be k prime of tau comma t times w of k of tau comma t. Sorry, not absolute value. Okay, so these steps can be done using various combinations of analytic and numerical approaches, depending on what parts of your design you can express with analytic functions. For example, if the target pattern is analytic, like a circ function, then you can analytically determine the k-space weighting function by taking the Fourier transform of the analytic expression of the function you're trying to excite. Numerical designs are more flexible in terms of the kinds of patterns you can specify. In this case, what we do is use an NUFFT operator to determine the k-space weighting function from samples of the target pattern in the image domain. So now that we've seen how we can relate an RF pulse to a target pattern in the image domain by first converting things to the k-space domain, we can start to talk about then designing two-dimensional spiral RF pulses that will require these mathematics. So to design a spiral RF pulse, we start by specifying the trajectory based on the desired spatial resolution, which determines the extent of k-space that we're going to visit, and the spatial field of view that we care about exciting over. So this determines the sampling density. So here's a depiction of a spiral trajectory in k-space, where the spacing between consecutive turns of the spiral is called delta k, and that is going to be equal to 2 times k max, the maximum k-space extent that we will visit, divided by 2 times n, which is the grid size in the image domain. And then the width is going to be 2 times k max, where k max is the maximum that we position that we visit on either side of the trajectory. This guy it has a point spread function in the imaging domain that is going to have a central sort of delta-shaped function, and then it's going to have its first side lobe some distance away from that. And the distance from the middle of the delta function to the first side lobe is the field of view. And here's the side lobe. And the width basically of that delta function here is delta r. It determines the smallest feature that we can possibly generate. So what we have to choose here in designing the pulse initially is we first have to set up the trajectory to achieve a certain delta r, and that is equal to 1 over 2 times k max. This again is the smallest excitable volume that we can achieve with this trajectory, or the minimum transition width that we can generate between a passband and a stopband. We also have to choose the field of view of the trajectory, which determines then the number of turns times delta r. I'm sorry, yes, n is the number of turns here, not the grid size. So n is the number of turns. Now choosing delta r is going to determine k max using these relationships. Then choosing the field of view, subsequently choosing the field of view determines the number of turns that we need n, how densely we have to sample in excitation k-space. So there are lots of methods out there, many MATLAB codes that are free online for designing spiral waveforms. So we're not going to go into detail in this course on how to design efficient spiral waveforms. But all of these methods will take the k-max and n that you give them, that is the maximum k-space extent you want to reach, and the number of turns you want, and they will spit out the 2D spiral waveforms based also on the maximum gradient amplitude that you can achieve with your scanner, and also the maximum gradient slew rate. That is the maximum derivative of the gradient that you can generate. Okay, so what we're going to start out now with is assuming that we've called one of these codes such that we have the trajectory waveform k of t and the gradient waveform g of t that generates the spiral. So these will be 2 waveforms, one for the x channel and one for the y channel, and we need to have both of these in order to design the RF pulse. And they have to both be then a function of time, which is what any one of these codes will give you. And we're going to use these then to design the weighting function w of k. Okay, so let's say that we want to have uniform k-space weighting to see the resolution limit. That is, if we have a pattern of ones that we're targeting in k-space, that'll give us a delta function in the image domain, so we can see just how fine a feature we can generate. So that would correspond to a k-space weighting of a rect function as a function of k-space radial location. So that'd be rect of kr over 2 times k max. So then our mxy of r would be 2 times k max squared, because you got to pull this out from the denominator, times a jink function, which is a Fourier transform of the rect function, of a radial rect function, which would be the jink of r over delta r, where jink is this first order Bessel function divided by 2r. So that's an example of an analytic excitation pattern. The jink function is slightly broader than a sinc function, but it decays faster with r to the minus 3 halves. So the first crossing is a little bit wider. It crosses at 1.2 instead of 1 for a jink function, but then the side lobes are a little bit smaller. We could also do a truncated jink weighting in the k-space domain, where we apply a jink as a function of k also to a rect function. Then what we'd get in the image domain would be a rect function convolved with a jink function. This then gives us like a flat plateau that we're exciting, right? So this is like exciting a disk, right? This is a plateau as a function of radial location, so it's like a disk that we're exciting. And then, of course, it's going to be convolved with a jink function that represents the blurring due to finite k-space extent. And so then the overall pattern that we're going to excite will then be a radial rect convolved with a jink function. So here's the k-space weighting that we would do. It's this jink function multiplied by the rect function as a function of kr. And if you take the Fourier transform of that, mxy of r is going to be this sort of plateau, but with some rippling across it due to the convolution with the jink function due to the finite k-space support. This delta r here is the minimum transition width that we can achieve given this spiral trajectory. We can also define a space bandwidth product, just like we have the time bandwidth product for one-dimensional slice-selective pulses, which is equal to the width in the spatial domain times the width in the spatial frequency domain. So this is again a normalized, a unitless metric representing the selectivity of the pulse. For the truncated jink weighting, the space bandwidth is 2n delta r times 2k max, which is equal to 2 times capital N, the number of turns that we have in the trajectory. And the difference between this and time bandwidth is that you can't count the zeros of the jink to get the space bandwidth product as you can with a sync, because it doesn't cross exactly at the right locations. But the large ripples in mxy make the truncated jink impractical anyways. So what we would instead do is a window jink weighting. So we would take a k-space weighting function that is a jink times a window function a, and so then in the image domain then, taking the Fourier transform of these two corresponding functions would give a rectangular function, again as a function of space, convolved with the Fourier transform of the window, which will have smaller side lobes than the jink function. So here in the k-space domain, we are, instead of multiplying by a rect as a function of kr, we are multiplying by a windowing function, and then that results in a function that has a wider transition width but has much smaller ripples. So we get a smoother response but double the transition width if we use a window function instead of the rectangular function. Okay, so again, to calculate the waveform, once you've got the weighting function that you want to generate and the k-space trajectory, you calculate, you take the known weighting function and the known the known gradient function, and you can get b1 of t by multiplying the gamma gt times the weighting function, right? The gradients, the amplitude of the gradients times the gyromagnetic ratio, and also times the weighting function sampled onto the trajectory. This does have to be scaled to produce the desired flip angle, so you can either do that by simulating it, integrating it, etc., to calculate the flip angle in the middle, and then you scale the pulse to get the flip angle you want. Overall, we can also give an intuitive interpretation of this, which is that b1 of t is a sample of w of k, the weighting function, at the trajectory location k of t, weighted by the speed along the trajectory. K of t, we should also note here that k prime of t, or the gradient amplitude, is an estimate of the density compensation function, d of t. This is adequate for single-shot spirals, but it's no good for interleaf spirals where we come back around multiple times. So if you do happen to have access to a better estimate of the density compensation function for such applications as interleaf spiral excitations, then you would use that in place of the amplitude of the gradient in designing the RF pulse. So next time we'll talk about practical issues of RF pulses and then echoplanar imaging, echoplanar type pulse design.